So our next example of related rates has a problem in which we're using an angle, theta. We're going to throw some trigonometry in here. So a radar base is tracking an airplane moving 2 kilometers per minute. So here's a radar base. In my little picture here. Radar base is here. Airplane is moving, and I've indicated the direction of travel. That must be indicated because that will make a difference in the working of the problem here. So our radar base is following this airplane traveling in that direction, and it's moving at 2 kilometers per minute, or kilometers per minute. The airplane is 5 kilometers above ground, and we're given that to be constant. So we're given this elevation here is 5 kilometers. That's given to be constant. The question says, how fast is the angle theta changing? So what's happening is this radar installation is following the airplane as it moves further and further away. This angle is getting smaller and smaller and smaller. Okay? So how fast is the angle changing when the airplane is 12 kilometers downrange? That is to say, given x is 12. So we're given this x value. We want to know when this x value is 12. And so express your answer. Oh, this is interesting. Express your answer in degrees rounded to 2 decimal places. Anytime you do trigonometry with the calculus, everything must be measured in radians. Everything must be measured in radians. Now, since we want our answer in degrees, what's going to need to happen is we're going to find a solution. That solution is going to be in radians, and then we will need to convert to degrees, and we'll go through that process. All right, so the procedure is the same as we've been working on for our related rates. We need to find, number one, what are we asked to find? What are we asked to find? How fast is the angle theta changing? We're asked to find the rate of change. How fast is it changing? Is the rate of change of theta. We're asked to find, we're asked to find the rate of change of theta, right? So that's going to be d theta dt, how fast theta is changing with respect to time. Now the question is, what are the degrees? What are the units going to be? Well, whenever we do calculus with trigonometry, theta must be measured in radians per, where's my unit time? Where's my unit time? Minute per minute. There's my unit time. So whatever unit time must be given in the problem. And one other little detail here. This is in radians per minute. I'm not asked for that. I'm asked to express my answer in degrees. And so after we find this, we're going to need to find d, I'm going to call it d alpha dt. So when I measure in radians, I'm going to call it theta. When I measure it in degrees, I'm just going to call it alpha. I don't want the same symbol to represent two different values. So theta is my radian, and I'm going to call alpha, I'm going to call d alpha, I'm going to call that the degree measure. So that's going to be in degrees per minute. And one last detail, as this plane is flying away, theta here is getting smaller and smaller and smaller. This is going to need to be a negative value. That value is getting smaller. All right. Okay, so what else? So that's what we're asked to find. What else are we given? We're given that the radar base is tracking an airplane moving. The plane is moving at 2 kilometers per minute. All right. So what is that? That is this distance. X is moving. This airplane is moving in this direction. So this distance is moving at 2 kilometers per minute. So that would be dx, how fast x is changing, 2 kilometers per minute. So we're given that dx dt. And is it getting larger? Yes, the airplane is moving in that direction. So it's getting longer at 2 kilometers per minute, right? This distance never changes, it's 5. How fast is the angle theta changing when the airplane is 12 miles downrange? When this is 12, when x is 12, we're given that right there. And that's all we're given. So now we need an equation to start with. Well, we got our angle, so we need to have a trigonometric equation. From our glory days back in trigonometry, we know SOHCAHTOA, so we know that tangent of theta is opposite over adjacent. And so we're going to start with tangent of theta is equal to opposite over adjacent. And what I'm going to do, I think most students tend to gravitate toward this. If you like, you can work through this also working with the quotient rule. I'm going to multiply both sides of this equation by x, because I'm going to write this using the product rule. So I'm going to prefer to use the product rule. You don't need to. If you want to continue to use the quotient rule, that's fine. You get the same final result either way. I'm going to go ahead and work this. And I think most students tend to gravitate toward the product rule. All right, so let's do our differential count. Differential count. Do we want dx dt in the problem? Do we want, there it is, dx dt? Yes, we do want dx dt in the problem. Do we want d theta dt in the problem? Well, not here. No, yes, d theta dt. Yes, that's the value we want. All right. So yes, the differential count is correct. And so now we're going to progress to finding the derivative. This requires the product rule. That's why I fix it this way. So the product rule says first times derivative of the second. More on that here in a minute. First times derivative of the second. Every time you do the derivative of a variable, you need d variable dt. First times derivative of the second plus the second, there's my copy paste, times derivative of the first. Derivative of the first is just 1, however, we need dx dt is equal to, so first times derivative of the second with dx dt, second times derivative of the first with dx dt, or d theta dt, dx dt, and then the derivative of a constant is 0. All right, got the derivative just like always. Now we're going to start to plug the values in and see if we can back solve and find d theta dt. So we need a value for x. Well, there it is, smacking it right in the face. So there's 12. We need secant squared, right? We need secant squared of theta. We don't have a theta. We don't have a theta. We don't have a theta. There's a variable value we need. In fact, what we need is secant squared of theta. We don't really need theta itself. We need secant squared of theta. We need this. We need secant squared of theta. This is very, very common. The derivatives of the trigonometric functions tend to be expressed in other trigonometric functions, one of which you might have handy, the other you don't. And so what we need to do is go back before the derivative. In fact, we go back to the original picture, and we need to take, okay, we got our value of x equals 12. What is secant? Secant, remember, secant is a reciprocal of cosine. Cosine is adjacent over hypotenuse. For secant, we need a hypotenuse over adjacent, which means we need to know that hypotenuse. As soon as we know this hypotenuse, we take that number, divide by 12, and square it, and that's secant squared. Say that again, right? We know this is 5. We know we want x to be 12. And then we can use Pythagoras to find this piece. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So we want the reciprocal. We want hypotenuse over adjacent. Once we find this hypotenuse, take that hypotenuse, divide by 12, and square it because we want secant squared. Hypotenuse over 12 is secant, square it. That's the number that we want right here. We want that number, we want that hypotenuse divided by 12, quantity squared. So what this devolves into is we need to do Pythagoras. And so we know 5 squared plus 12 squared is equal to, let's call this z squared. And it's not very hard to show that if you do that work, I trust you can handle that. Z works out to be 13. All right, so this works out to be 13. Secant is hypotenuse over adjacent. Secant squared is hypotenuse over adjacent, quantity squared. So I want hypotenuse over adjacent, quantity squared. And now we continue merrily along our little way. D theta dt is what we're looking for. Tangent theta, smack you right in the face. Tangent is opposite over adjacent. Dx dt is somewhere here. Dx dt is 2. Solve for d theta dt. And that's not particularly challenging to do. Let's see, this is, it doesn't really matter how you do that. I'm going to go ahead and do this in my head here. That's 169 over 12, because this 12 cancels with one of those. Is equal to, when we subtract this to the other side, 5 times 2 is 10, negative 10 over 12. And so now if we subtract this to the other side, right, subtract this to the other side of the equation. I'm sorry, not subtract. I just said that wrong. We don't subtract that to the other side of the equation. We need to divide. Divide both sides of the equation by 169. How do you divide by a fraction? The way you divide by a fraction is you multiply by the reciprocal. And so d theta dt, I just said that wrong, d theta dt is negative 10 over 12 multiplied by the reciprocal. That's times 12 over 169. The 12s cancel. And so what we end up with is negative 10 over 169. And that is in radians per minute. So that's negative 10 over 169 radians per minute, which is, I don't know about you all, but that's particularly unhelpful for most people. So what I'm going to do, the last piece, is I'm going to convert this from radians into degrees. And I'm going to go ahead and steal some space up here. To convert from radians to degrees, I always just use pi is equal to 180. So pi, I just set up a proportion. Pi is to this 10 over 169. Might as well throw the negative in there. 10 is to this, as 180 is to don't know yet. Cross multiply and set them equal and solve. And if you do that, you get pi times x is equal to 180 times negative 10 over 169. Divide both sides by pi. So I'm going to clear the pi out. So you can convert from radians to degrees however you want to convert from radians to degrees. If you know a formula, that's wonderful. I just set up this proportion every time. Pi is to this in radians as 180 is to don't know yet in degrees. And then just cross multiply and solve that out. And let's see if I can now work this out. It's going to be negative something. It's going to be, what I have here is 180 times 10 divide by 169. What's that equal to? And then I'm going to divide that by pi. And I have 3.390. And how many decimals? I want 2 decimals. And so this is now approximately equal to 3.39 degrees per minute. And what that tells you is that's fairly slow. 3 degrees, almost 3.5 degrees per minute, that's pretty slow. Well, it tells you because this thing's way down range, it's not changing very fast, that angle of elevation. All right? So that's the procedure, and it's very straightforward. Just as a matter of, by the way, this is 100% by the way. If I had not changed this into product rule, this is how it would have looked. The derivative of tangent is secant squared of theta, d theta dt is equal to, and then we have denominator times derivative of the numerator, that falls out, minus numerator times derivative of the denominator, all over denominator squared. And it's not obvious, but if you throw all this information into this equation, this falls out. So I have secant squared of theta, d theta dt, is equal to negative 5 dx dt over x squared. It's not obvious, but if you throw all that information into here, you get the same final result that we did. So it doesn't matter if you use quotient rule or product rule. In fact, we should go ahead and do that. We already have secant squared of theta. We've already computed it once. It hasn't changed. So that's 13. Now let's make that better. 13/12 quantity squared d theta dt is equal to, this is 5 times, what is that? 5 times dx dt. Dx dt we said was 2. So this is negative 10 over x was given to be 12. So let's make that 12 squared. And then if we multiply by the reciprocal, right, multiply by the reciprocal, this is d theta dt is equal to negative 10 over 12 squared. Multiply by the reciprocal, that's 12 squared over 13 squared. The 12 squareds cancel, and that's negative 10 over 13 squared is 169, which is the same thing we had before. So it doesn't matter if you use product rule or quotient rule, you get the same final result either way.